Can you hear me now? Cool. Said I am not yet recording, but I guess it was class time, and so I was saying y'all are getting amazingly reliable at this point in your reminders. It's too late, Julie. Somebody already said it. All right. How's everybody's weekend? Everybody do anything fun? Nothing? Our Washington football teams beat the Dallas Cowboys, so that's good. Watch the Dodgers win Game 5 in Texas. Who's a Dodgers fan? Didn't think anybody outside of LA was a Dodgers fan. It was your dog's birthday. That's good. Amber painted a mural. That's awesome. Esther, I'm sorry. It was awful. Hopefully it gets better. Can you math hard? I assume you mean stats because that's the only thing that matters. He started and finished good for you. Okay. Yes. See, anybody who likes the Dodgers has to be from LA. All right. Let's go ahead and get started. But first, what did we learn last time? And while we're saying that, I'm taking off my sweater because it's 1,000 degrees in here.
Repeated measures, F.
Yes.
Variance, sorry.
Exactly. So we learned repeated measures. And why does repeated measures ANOVA test even exist? Like, why is that a thing? And it shouldn't be. It's not an answer.
And so that you can test the same subjects, but there's multiple tests.
Yes. So there's multiple tests. And how many?
More than two. Or more, yeah.
More, yes, exactly. So in theory, you can actually run an ANOVA with 2 samples, but it's typically used when you have 2 or more, or excuse me, 3 or more samples. All right, so what did we learn about a repeated measures ANOVA?
There's a whole other factor now with the p-values.
Yes, exactly. So in this case, when we say P, what do we mean? Like, what does P stand for?
Personal totals of scores.
Exactly, yes. So let's say we have condition 1, condition 2, and condition 3, and then we have subject 1, subject 2, subject 3, subject 4, and each participant has data for each of these. Move that over. And so whereas the T that we've been using before has been essentially that column total, that condition total, the P value is the participant, right? So you get your T down there, you get your P up here, and this is distinctly different from the typical P value, right? So when we say P, we don't mean P value, we mean P, like the person total, or participant total. Perfect. What else? Yeah, so why do we have a between subjects variance?
It helps us calculate our sum of squares error.
Yeah, exactly. So our sum of squares error, and why do we even have to go through that other step? Yes, because it's the same subjects, exactly. Because it's a repeated measures test, we need to establish what are the variances that we're seeing between the conditions that are not necessarily between the subjects, right? Because every participant acts as their own control, we have to account for that and remove that source of variance. Questions about what we covered last time? Awesome. Awesome, awesome, awesome. All right. Here is your fun fact of the day. Cookie Monster's name is Sid. I don't know why they never use it. Here's a bonus fun fact. The person that voiced Miss Piggy also voiced Yoda. There you go. Listen to that. They sound very similar. All right. So today we are talking about two-factor designs. In the context of an ANOVA, an independent variable, so the variable you are manipulating, or it can be a quasi-independent variable, so a variable that changes just naturally, but you can't assign it, is called a factor. It may also be Fozzie Bear, but it's definitely Miss Piggy too. And research studies with two factors are called factorial designs, or simply a two-factor design. So, an example of a two-factor design would be us looking at self-esteem and whether there's an audience on how many errors you make during a speech. All right, so one factor is esteem, and we're manipulating that, we're operationalizing that as high and low and maybe a self-report. And then the other factor is the no audience or audience manipulation. You can see it's represented the same both up here. And so why might we want to do a two-factor ANOVA in lieu of just a one-factor or repeated measures? What benefit is afforded to us by doing a two-factor ANOVA?
I guess we can group the different data sets, or I guess we can get a better hypothesis from, I don't know how to describe it. We can group our different data sets into individual data sets and then like get a null hypothesis for each one, possibly.
Yeah, I think you're onto the right path here. The benefit of doing a two-factor analysis is it provides us a lot better picture of what the real state of the world is, right? So let's say we didn't have self-esteem as a manipulation and we just had no audience versus audience. Well, the effects would be somewhere between, so these two would be averaged and then these two would be averaged, and we would get a smallish effect, right? It would be right in the middle of those two. But in reality, it's not just the fact that an audience increases the number of errors. That does what we call interact with one's self-esteem, right? So for those with high self-esteem, having an audience doesn't matter, right? There's no effect whatsoever. If you have high self-esteem, talking in front of 1,000 people doesn't matter. However, if you have low self-esteem, you have a much bigger effect, or even an effect, for audience. right? And so if we didn't have the self-esteem, you can see how these would be averaged together. And we would say, okay, well, it appears that having an audience must make people nervous and increases the number of errors, right? But the inference there is that it must be the case for everybody. But what this data is showing us is that it's not the case for everybody. It's only those with low self-esteem that get nervous. And it tells us that those with low self-esteem, on average, commit more errors than those with high self-esteem. All right, so you can start getting a much better nuanced picture of the ground truth of the world. And so let's say I wanted to see, I forget exactly what this example is, but let's say I wanted to see how good your athletic output was at different temperatures and different humidities. All right, and I want to see what the interaction is here. So I have one group who I put in an 80-degree room with low humidity. And then another group in a 90-degree room with low humidity, and then a third sample in a 100-degree room with low humidity. And then I do that for high humidity, 80 degrees, 90 degrees, and 100 degrees. Right? And so the benefit is it allows me to see if there is a difference between humidity, such that does humidity affect people's athletic performance. It also allows me to see if there is an effect of temperature on athletic performance. But then it also allows me to see the interaction. Maybe humidity only really affects people when it's 90 or 100 degrees in that room. Right? Maybe there's no effect for humidity when it's 80 degrees, and temperature doesn't really affect athletic performance if there's low humidity. But when you get to high humidity and high temperature, then you start seeing a performance effect. So notice that that study involves 2 levels of humidity. So factor 1 humidity, 2 levels, and 3 levels of heat, and 1 burp, to create a 2x3 matrix with 6 different treatment conditions. All right, so this is 80-degree low humidity, 90-degree low humidity, 100-degree low humidity, right? Those are 3 different treatment conditions, and then we do that for high humidity. And so when we're representing this, we put each treatment condition in a different cell in that matrix. Questions about this so far?
So I'm trying to figure out how to identify that it would be 2-factor. So is it basically if we have, I guess, 2 different large categories that we're measuring, but with 1 sample set?
It would be 2 different independent variables. And
Okay.
so let's say we wanted to look at, the effects of being an early riser versus a night owl, and being a freshman versus a senior on caffeine consumption.
Okay.
Question came in, is this something that can be used in genetics? So I'm not sure specifically what you're talking about. But yeah, this is something wherein you're looking at different genetic manifestations, right? This is, sorry, I've got a hair. It's hard to get it through the mask. But yeah, see where you start looking at different genetic manifestations and either their behavioral correlates, So predicting physical characteristics. Yeah, so you could absolutely do this, right? And so, for example, we have malnutrition as one factor. So, people who are malnourished versus fully nourished. And then another one we could have is that genetic aspect, right? So gene A versus gene B. And we see that interaction such that, maybe. All right. So everything done up to this point with ANOVAs has been a function of just a general main effect, right? There's a difference between groups. 3 or more groups when you're running in ANOVA, and ANOVA won't tell you what difference is or is not a difference between those groups. Significant F means that there was a difference between those heat conditions, but it doesn't tell you which one was significantly higher, which one was significantly lower. We're going to do post hocs, I think next class. And that's where we'll start getting at what are those actual significant differences between the groups. But everything else has just been, okay, there is a difference between these. A two-factor ANOVA, we now have 3 different potential significances. We can have a main effect for factor 1 or factor A. We can have a main effect for factor 2. And then we can have an interaction between those, right? And so this is saying what I was saying here. You could have a main effect for humidity such that performance, but temperature doesn't. You could add temperature on top of that. You could have a main effect for treatment B for the temperature. So temperature affects performance, but humidity doesn't. They could both be significant. So both humidity and temperature affect that difference. And then the third thing is that interaction. So again, your results are not only where you are on factor A, but also
Professor.
Yeah. Oh, it looks like it's breaking up for you.
Yeah. It's pretty choppy.
Has it been choppy the whole time?
It was okay at first, and then it started getting choppy as you started going along.
Okay. All right. I don't know why it's choppy. It may be the Wi-Fi here. Let me. All right. Hold on. I'm going to switch over to the computer and see if that helps. Can you all hear me? Cool.
Yes.
All right. So I'm going to lecture from here. If it's still choppy, let me know, and we'll figure out what plan C is or whatever plan we're on. But yeah, it seems to be okay from this end, at least in terms of the recordings. So, all right. That's not what was supposed to happen. All right. So we went over that. Cool. All right. So just to reiterate, you can have a main effect for example, humidity, so there's a difference between these groups. You could have a main effect for temperature, such that there's a difference between these groups. Or you could have an interaction, such that where you are on, let's say, humidity, and where you are in the temperature has a main effect, or excuse me, has an interactive effect, such that maybe humidity only matters when you're in the higher temperature rooms. All right, so that's what this is just saying, right? So you could have a main effect for A, right? These means are different, these means aren't. You could have a main effect for B, these means are different, these means could be different. And then you could have no effect for either one of them, right? Such that the means are the same there, and the means are same there, but you have an interaction such that you can see your position on A flips on level 2 for condition B. So we'll go over some examples in just a minute. So again, as with everything we've done so far, the goal for this two-factor ANOVA is to determine whether the mean differences that are observed for the sample data are sufficiently large to conclude that they're significant differences and not simply the result of sampling error, right? We're always going to find differences between groups. We want to know if those differences are statistically significant. I accidentally touched my mask with pizza hands earlier today, and now my face smells like pizza. Pretty great problem to have. It's better than when I take a Mentos and then accidentally breathe menthol into my eyes and start crying in public. All right. So to evaluate the sample mean differences, a two-factor ANOVA conducts 3 separate independent hypothesis tests. I think we all do, Julie. So the first test we're evaluating is the main effect for factor A. So again, like I said, comparing the overall performance with high humidity versus the overall performance with low humidity, right? In this case, we're just collapsing across the levels of temperature. We're just looking at humidity. The second one would be the main effect for factor B. So the mean differences between the levels of factor B would be looking at the different temperatures such that temperature affects performance when collapsing across levels of humidity. And then that third and final is the interaction. So your performance suffers at high humidity in, let's say, the 90 and 100 degree condition, but it doesn't in any of the other 4, right? So that would be an interaction. Questions on that? Awesome. once we get through today, you will be able to do enough statistics to kind of fake your way through graduate school if you didn't learn anything else. I'm not recommending you don't learn anything else, and you still will be tested on everything else, but I'm going to still give you that opportunity. All right, so this again is going to be a two-stage process such that we have our total variance, our total sum of squares, and then our total mean squares, right? So mean squares total is just that total variance. That can be split into the within treatments variance, so mean squares within. And then mean squares between treatments. And then the between treatments variance is the sum of the variance of factor A, so in this case, the variance of humidity, the variance of factor B, aka the variance of temperature, and then the interaction variance. So the variance, which is inherent in that interaction term we were talking about. So again, like I've already said before, the primary advantage of combining two factors or two of these independent variables in a single research study is it allows you to examine how the two factors interact with one another. This interaction can be defined as extra mean differences beyond the main effects of the two factors. And another way of thinking of this is that the effects of one factor depend on the levels of a second factor. So who can think of a real world example of an interaction between two factors?
I don't know, mixing ammonia and bleach.
Okay.
Mixing two different, components. I don't know.
Yeah, and so I think that's a great example in the sense that just ammonia by itself at low levels is perhaps not as bad for you as inhaling a lot of ammonia or ammonia at high levels. So you have a main effect of ammonia concentration. You could then have a main effect of bleach concentration such that, you know, inhaling small amounts of fume of bleach is not that bad. Inhaling a lot of fumes of bleach is really bad. But then you add that interaction such that if you were to add the two of them together, at every level, that could potentially be bad. But at the highest concentrations, that's spectacularly awful.
Or like, I think a better example is maybe if you mix alcohol with a prescription medicine, like, or aspirin even, for example.
Yeah, exactly. So yes, anytime you're interacting, you can think of these as like drug interactions, but they don't have to be drug interactions. So let's say we were interested in predicting students' overall levels of boredom in the classroom. And so one factor would be the year they are in school. So freshman through senior. And then another factor would be whether it's a major class or just a general purpose class, right? Such that maybe the older you get, the more bored you get. Maybe if it's your major class, you're less bored than a non-major class. But that interaction is such that seniors in their non-major classes are literally bored to tears, right? So at that really extreme example. So each of the three hypothesis tests in the two-factor ANOVA will have the same F ratio or excuse me, the same basic structure, not the same F ratio, the same basic structure. Right? If our general one-factor F ratio was mean squares between over mean squares within, it's going to be a similar concept moving forward. All right, so each mean square value, once again, is the sum of squares of interest divided by the degrees of freedom of interest. And the individual sum of squares and degrees of freedom values are computed in a two-stage analysis. So like we already showed, that first stage of the analysis is identical to that single factor ANOVA, that first ANOVA we did, and separates the total variability, sum of squares and degrees of freedom, into the two basic components between treatments and within treatments. But that between treatments variability measures the magnitude of the mean differences between the treatment conditions, aka the individual cells in that matrix, and is computed for using, or excuse me, and is computed using the basic formulas for sum of squares between and degrees of freedom between, like we've gone over before. So that sum of squares between is the sum of t squared divided by n. All right, so you're taking every column total, you're squaring it, you're dividing it by the number in that column. From that, you're subtracting G, that grand total, so adding every data point together and squaring it, dividing it by the total number of observations. And that degrees of freedom between is the number of cells or the number of totals, the number of T's you have, minus 1. So in our heat and humidity condition, that would be 6 minus 1 or 5. Yeah, so it's between treatments, yeah. Zoomies, is this better or is it still breaking up?
Much better.
Good. So the within treatments variability measures the magnitude of differences within each treatment condition or cell and provides that measure of error variance that is unexplained, unpredicted differences due to error. Right? And so this is the exact same approach as we've done so far, right? The mean squares within is just the sum of the sum of squares. So you get the sum of squares for every individual cell, and then add them all together, divide them by the degrees of freedom for every individual cell. And all three F ratios, right? The ratio for main effect for factor A, the F ratio for main effect of factor B, and the interaction effect, whoops, are going to put that mean squares within on the denominator of that ratio. So the only thing you're going to be changing in that ratio is what goes on top. What goes on top is what you're interested in. So as we've already said, the second stage of the analysis separates the between treatments variability into three components that will form the numerators of those three F ratios. Variance due to factor A, so mean squares factor A. Variance for factor B, so mean squares factor B. And the variance due to the interaction. So each of these three variances, again, for whatever reason we call variances within ANOVA mean square, measures the differences for a specific set of sample means. That main effect for factor A, for example, will only measure the significance between, for example, the rows of that data matrix. So in this case, a significant main effect for factor A would be a significant difference between the humidity conditions. And this is just regurgitating what we've already said before. Last time, right? We're relying on the sample totals rather than the sample means. Right? So the T's rather than the means. So again, sum of squares between is the sum of T squared divided by N. So you're taking every T, you're squaring every T, you're dividing it by the number in that cell. And you're adding that to the next cell's T squared divided by the number in that cell. All right, and so you could just represent this the same way. It's just that total squared divided by the number minus G, that grand total squared, divided by the total number of participants. This isn't saying anything new, just regurgitating. For factor A, the totals are the row totals, and the degrees of freedom equals the number of rows minus 1. So what would be the degrees of freedom in that humidity and temperature example if humidity is factor A? So factor A is humidity, degrees of freedom for A is just 1, right? 2 rows minus 1 gives us 1. What would the degrees of freedom for factor B be? 2, exactly, yes. 3 different levels minus 1 is 2. Oof, I went back a long way there. Yes, good job, Amber. The interaction, again, measuring that extra mean differences that exist after the main effects for factor A and factor B have been removed. The sum of squares and degrees of freedom values for the interaction are found by subtraction. Right, so to find that sum of squares interaction represented AXB, which sounds like the name Elon Musk is going to give his next child. y'all don't get that reference, go look up Elon Musk's child's name. The degrees of freedom values, again, are going to be the degrees of freedom between cells minus the degrees of freedom A minus degrees of freedom B. All right, so let's work out an example here. I know this looks like a lot of mess, and it kind of is, but let's walk through step by step here. All right, so let's go ahead and say that factor A is that humidity condition. All right, so this is low humidity, A2 is high humidity. Factor B is going to be the temperature, right? So here is 80, here is 90, and here's 100 degrees. And then for each combination, for low humidity at 80 degrees, we have data. All right, so we have 5 different data points in here, 5, 3, 3, 8, 6. These are the participants' performance scores who are in the low humidity and 80-degree temperature condition. For low humidity and 90-degree temperature condition, we have 5 participants, scores 9, 9, 13, 8, and 6. For 100 degrees and low temperature or low humidity, excuse me, we have 5 more, etc. So for each one of these cells, right, for these 6 main data cells, up here and then here, we can calculate a t value and the sum of squares for each one of these cells. So to get the sum of squares, we're just using that same sum of squares equation we've always used, which is what?
Sum of x squared minus sum of x in parentheses squared over n.
Exactly. This is much harder to do on my computer trackpad, but bear with me. So the sum of x squared, so square every x and add them all together. So 25 plus 9 plus 36 plus 9 plus 64 minus the sum of x. So 5 plus 3 plus 6 plus 3 plus 8. Square that value, divide it by n, or in this case 5. So again, we're finding the sum of squares for every individual cell. We're finding the t for every individual cell. And then we can find the column totals and the row totals. All right? The total for A1 is 90, 25 plus 45 plus 20. Five plus 5 plus 20 for 30. Column totals, 25 plus 5 for B1. 45 plus 5 for B2, 20 plus 20, 40 for B3. We then find our big N, which is the total number of observations. So in this case, we have 6 cells, and in each cell, we have 5 people. So that gives us 30 total observations. The G we get by adding up all the data from all 6 cells, or you can make it easier on yourself and just add A1 to A2, or B1 to B2 to B3. It'll all come out to 120. One mistake I see is that people will add B1 to B2 to B3 to A2 to A1, and that gives you double what you need. You don't do that, right? Either A1 to A2 or B1 to B2 to B3, or just take every individual data point and add them all together. And you get 120. And then that sum of x squared, you're squaring every one of these data points and adding them all together. And then we're ready to rock and roll. Questions about this so far? And it's just the total number of observations, right? And so it's how many single data points are there in all 6 cells.
So if we add up all of those, the 90, 30, 30, 50, and 40, that'll give us double, you said, right? Of
Yes.
the G. So can we just still use that and just divide it by 2 though?
You're just
Or is
creating
that
extra work for
unreliable?
yourself. I wouldn't do that.
Okay.
So
Okay.
just add these together, right?
All right.
Perfect. I mean, you could do it, but seems like a recipe for disaster.
Just to clarify on the SS between, it's sigma of each t squared divided by lowercase n first, and then minus g squared over capital N, right?
Correct. Yes. And we'll go over that in just a second. We'll calculate it.
Okay.
All right. So let's find our degrees of freedom for everything. Our degrees of freedom total is the same as we've used before. N minus 1, big N minus 1. In this case, 30 individual data points minus 1 gives us 29. Our degrees of freedom between, as we said earlier, is the total number of cells minus 1. Or in this case, 6 minus 1. The degrees of freedom within is going to be big N minus K. Right? And K in this case is going to be the number of cells. So 6, once again, 30 minus 6. And then we've already done the degrees of freedom A, which is the number of options, or the number of levels rather, in factor A. So 2 minus 1 gives us 1. Degrees of freedom B, the number of B minus 1 is 2. And then our degrees of freedom for the interaction is that degrees of freedom between minus degrees of freedom A minus degrees of freedom B. Or, where are we? We're getting that 5 from up here minus 1 from here minus 2 from here. All right, so that total sum of squares is that sum of x squared that we calculated before minus g squared, that grand total squared divided by the number of observations. So 820 minus 120 squared divided by 30 gives us a total sum of squares of 340. Within subjects, sum of squares is again just the sum of the sum of squares. Right, so we go back here, we have 18, 26, 20, 8, 20, 28. So we add those up, 18, 26, 20, 8, 20, 28. Add those all up, you get 120. This is just a coincidence that this is the same value as G. Don't read into that. That's not going to be the case all the time. Then for our between subjects sum of squares, as Caleb said, it's the sum of every t squared divided by n. And then from that sum, you are subtracting the grand total squared divided by big N, or the number of observations. So total 1 is 25. The 25 squared divided by the number in this cell, or 5, plus total 2 is 45 squared divided by the number of observations in cell 2, which is 5, plus 20 squared divided by 5, plus 5 squared divided by 5, and so on. You're going to add all of those up. And then from there, you're subtracting that grand total, that G of 120 squared divided by 30. And so that gives us a between subjects sum of squares of 220. Right, so at this point, it should look very familiar, right? This is pretty much the same thing as we would have done in the one factor. We just have more cells to do it for. Now's the fun part. Now we're finding the sum of squares for factor A. And that's going to be the total, the sum of each t for factor A divided by the number in each level of factor A, minus still that grand total squared divided by that big N. So what am I doing here? This is the t for A1. So 90 squared divided by 15, because there are 15 individual data points in just this row alone, plus 30. So that's the sum of this row divided by the number in that row, again 15. Minus big G, a grand total squared, divided by 30. Gives us 120. Again, don't read into the fact that this is the same as G. This is just a weird coincidence. And then for sum of squares B, we're doing the same thing. Now we're just doing it with all the columns. Right, and so 30 for column 1 squared divided by 10, so the number of observations in that column. Crap. Plus 50, which is the total for column 2, divided by 10, or squared, excuse me, divided by 10. That's 5 and 5. Plus 40 squared divided by 10. Minus again that G squared divided by 30. Gives us 20. And then to find that interaction term, we're taking the sum of squares between that we already found. From that, we're subtracting 120 for that sum of squares A, factor A that we found up here, minus that sum of squares factor B that we found here. And that gives us a sum of squares for the interaction of A and B of 80. Questions so far? Everybody feeling pretty good about it? Pretty straightforward. It's just more work. So again, that mean squares for the factor of interest is just going to be a function of the sum of squares for that factor divided by the degrees of freedom for that factor, right? Same thing as we've always done. Mean squares equals sum of squares divided by degrees of freedom. If you're interested in factor A, take the sum of squares factor A divided by the degrees of freedom factor A. Interested in the interaction, the sum of squares of the interaction divided by the degrees of freedom for the interaction. That mean squares within, as always, is that sum of squares within treatments divided by the degrees of freedom within treatments. So again, this is the same as we've always done, just reiterating. Mean squares is always sum of squares over degrees of freedom. All right, so let's plug everything we've just done into a table. All right, so we have the sum of squares between treatments of 220, and we know it has 5 degrees of freedom. Right, number of cells minus 1, 6 minus 1, 5. Factor A, we found, has a sum of squares of 120. It's the number of levels in factor A, so 2 minus 1 gives us 1. For factor B, our sum of squares was 20. Our levels of factor B was 3 minus 1, or 2. Our interaction, sum of squares was 80. And our degrees of freedom, again, is going to be 5 minus 1 minus 2, or 2. Our within treatments sum of squares was again 120 with the degrees of freedom of 24. So again, this was big N minus K, or big N minus the number of cells, 30 minus 6. And then our total sum of squares was the, or we got our total sum of squares, excuse me, I don't know where my head just went. And then we have our degrees of freedom for total, which is just big N minus 1. 30 minus 1 gives us 29. And so as with before, you see that the total sum of squares is a function of the between treatment sum of squares plus the within treatment sum of squares. The total degrees of freedom is just a function of the between treatments degrees of freedom plus the within treatments degrees of freedom. All right, the between treatments sum of squares is a function of these three added together. And the between treatments degrees of freedom is a function of these three added together. To find our mean squares for each value, we're going to take that sum of squares divided by the degrees of freedom. So 120 minus 1, 120. 20 divided by 2 is 10. 80 divided by 2 is 40. 120 divided by 24 gives us 5. And so now we need to calculate our F values. So our F value for factor A is what? How do we calculate that?
The degree, oh wait, never mind. It would be the MS between over MS within, right?
not MS between over within. It would be MS for the factor that we're interested in over MS within. So if we're interested in the F for factor A, it would be mean squares A divided by mean squares within. 120 divided by 5 gives us 24. For factor B, how do we get our F value?
MSB over within treatment. Sorry, factor B, yeah.
Yes, yeah. So the mean squares for factor B over, again, that mean squares within treatments. So 10 divided by 5, 2. And then for that interaction, once again, we're taking that mean squares of the interaction divided by that mean squares within gives us 8. So we're going to have 3 different F values for this that we then have to compare in the back of the book. But again, let's say on the exam, I took away some of these values and I told you to fill it in just based off of the rest of the values on the table. You should be able to do it, right? You should be able to know how everything is relating to one another on this table. Questions about that? I had students last year when I gave them this type of practice, or when I gave them this type of problem on the exam, who wrote, "You can't do that." Not telling me well, presumably not telling me I wasn't allowed to ask them that question, but saying that there wasn't enough information. I promise if I'm giving you that type of problem, there is enough information to fill it out. So. All right, so we have our main effect of factor A with an F value of 24. We have our main effect for factor B with an F, whoops, this is supposed to be B, and this is supposed to be the interaction. So our main effect of B was an F value of 2, and our our F value for the interaction was 8. So now we have to figure out if we're rejecting the null or retaining the null for each one of these. So we go to the back of the book. I am once again in Appendix B, and I am in the F table. So you'll notice we have these 2 degrees of freedom once again. It's always going to be degrees of freedom numerator divided by degrees of freedom denominator. Right? And so if I have factor A, to get that F value, it's mean squares factor A divided by mean squares within treatment. So the numerator degrees of freedom is 1, the denominator is 24. For factor B, it's mean squares factor B divided by mean squares within treatments. So the degrees of freedom numerator is 2, denominator is 24. Same thing for the interaction. It's that mean squares interaction divided by mean squares within treatments, or degrees of freedom interaction for the numerator, degrees of freedom within treatments for the denominator. So we're going to the back of the book, that F distribution. So for the first one, we're going to look it up. Degrees of freedom for the numerator. We're going to that first column because we only have 1. From there, we go down all the way to 24. In this case, I have to turn the page. Staying in column 1, go down to 24. And again, I have a light-faced and a bold-faced type. Light-faced is 0.05. The bold-faced is 0.01. So let's say we're testing at the 0.05 level. So the F critical, or F crit, for 1 degree of freedom in the numerator, 24 degrees of freedom in the denominator, at the 0.05 level is 4.26. So do we reject the null or retain the null for factor A?
Reject.
Yes, we reject, right? Because this value is greater than that F critical. So what this is saying is there is a main effect for humidity on people's performance, right? Irrespective of temperature, we're saying at different levels of humidity, there are differing levels of performance. So now on to factor B. So this time we have 2 degrees of freedom in the numerator and 24 still in the denominator. So we go down to that cell, and that says at the 0.05 level, our F critical is 3.40. So do we reject or fail to reject? / fail to reject or retain would be the same thing. But do we reject or retain the null hypothesis?
Retain.
We retain the null hypothesis, right? Because this is smaller than this. So in layman's terms, this is saying that there is no effect for temperature on performance. Doesn't matter how hot it is in the room, performance is unaffected. We now have the interaction, and because it's got the same degrees of freedom, we know that the F critical is the same. So, do we reject or retain the null hypothesis?
Reject.
Reject, exactly, because our F value is greater than that F critical value. And so what this says is that there's an interaction between temperature and humidity on performance. We don't know where that effect lies. We just know that they're interacting with each other, right? It's a more complicated picture than just saying there's a main effect for temperature and there's a main effect for humidity. And so we'll talk about post hoc tests next time, but we can even go and just look at this, right? And so we can kind of see what that picture looks like, right? So you've got 25 here, you've got 45 here, you've got 20, and then 5, 5, 20, right? So there was no main effect for just that heat, that temperature rather. There was a main effect between the humidity. And then you can see that at 90 degrees and low humidity, seems like we have higher performance. At high humidity but lower temperatures, we have lower performance. Right? So you can start seeing how this paints a little bit more of a complicated picture than just heat effects or just temperature effects. It's that interaction between the three. Questions about today's lecture? About two-factor ANOVAs. What do you mean? From this? Yeah, so you're just looking at, okay, what is the total for the performance, right? And so we know we have a main effect for A based off of our data, such that low humidity tends to perform higher than does high humidity. We know that there is no main effect for B, so temperature doesn't matter. But we know there's a significant interaction, right? Such that what cell you're in, which is a function of both the temperature and the humidity, results in different effects, right? So you can see performance was essentially twice as high in this cell as it was in this cell, this cell, and this cell, and nearly, well, and it was 9 times higher than it was in this cell and this cell, right? So you can start to see how you have a little spike in performance here, and you have dampening in performance here, right? And that's much more complicated. You can't just say it's a main effect of temperature, because temperature is the same here, and you've got high performance here and low performance here, right? And you can't just say it's a difference between low and high humidity, because at high temperatures, low and high humidity essentially seem to be having the same overall effect, right? So this isn't scientific what I'm doing here. This is just to kind of illustrate what an interaction actually is. So we'll go over the post hoc test for actually making those comparisons. All right, I will hang out here if you have any other questions. Otherwise, have a lovely Monday, and I will see you all on Wednesday.
Is this something that is used as well to look at like positive reinforcement versus positive punishment and negative reinforcement and negative punishment? I forgot what that.
Yeah,
What
the
that
operant
is.
conditioning.
Yeah.
So explain to me your reasoning. Why would this be used for that? Are you thinking
to
like
see.
you would have positive, negative reinforcement and punishment?
Mm-hmm.
Yeah. Yeah, exactly.
Yeah.
Yeah, you could use that for this.
Okay.
Yeah, great thinking. Sure. So again, the mean squares is just like we've always done, right? So the mean squares is always just going to be the sum of squares of what we're interested in divided by the degrees of freedom of what we're interested in. Right? So the mean squares for factor B is just sum of squares factor B divided by degrees of freedom factor B. Interaction, sum of squares divided by degrees of freedom. So the F ratios are going to be a function of whatever factor we're interested in, that mean squares always divided by mean squares within treatments. So F for factor A is going to be mean squares factor A divided by mean squares within treatment. So 120 divided by 5 gives us 24. Our F for factor B is mean squares factor B divided by within treatment. So 10 divided by 5, 2. Make sense? Of course.